Oye, and welcome back. In this video, we're going to be looking at the STK side of some of the applications for our B series for QR1. In particular, we're going to be looking at length at scenario 1B1, which is solar spotlight, but we will also be talking briefly and take a brief look at 1B2, which is relay delayed, that once again returns to the Earth as the central object. So in the first one we'll be taking a look at, we have the Moon as our central object. We've got the Earth there in the background. Now, it's a common misconception that the Moon has a dark side and a bright side, implying that one side is perpetually dark and one side is perpetually light. We could say that this right now is the dark side of the Moon, but in 2 weeks' time, based on the Moon's orbital period, this side will be the one that is actually lit up. So at any given point, you could correctly say that there's a dark side of the Moon and a light side of the Moon, but it's not always the same side per se, because as it orbits around the Earth through the course of 1 month, we'll actually have the sides switch, which side is lit up versus not. So we don't have perpetually one side that is always dark. We do, because it's tidally locked, have one side that is permanently faced towards Earth. So we only see one side of the Moon. There is a back side of the Moon, or far side of the Moon, and that would be an appropriate thing to say, because that would be the side that is away from the Earth, and that is always the same side, because we always see one side of the Moon. It looks something like this from Earth. And so the far side looks noticeably different, but we never see that from Earth because it is tidally locked, as is described in the mission brief. Okay. Our goal in this scenario is actually an interesting one, because what we're going to try and do is we want you to imagine that each of the satellites has a bunch of mirrors on them. So on our Moon, we've got it where if we were to set up an installation, say a greenhouse of some kind, that could collect energy from the sun, just using sunlight, we might actually be able to grow some plants on the Moon to help support a possible colony of humans living there. The problem is most of our plant life is actually adapted to what happens on Earth, which is going to be where we have sunlight for about half of a day, so you'd be looking at maybe about 12 hours worth of sunlight on it, and then 12 hours of darkness. The plants might be happy about getting 24 hours a day sunlight when it's on the side pointed towards the sun, but they probably won't be happy for going 2 weeks without any sunlight whatsoever. So in this case, our goal is to try and redirect sunlight in a way that we could try and get it pointed onto the greenhouse, even when it's on a not favorable side of the orbit. This would be especially important if we could set up colonies deeper in our solar system, farther away from the sun, because the sunlight there, the way light works, would end up much weaker, for want of a better term. It's kind of like if you're looking at a light, say a lamp in the living room, and if you get real close to it, it can hurt your eye. Don't actually look at it super duper close. It seems very bright. But if you go across the house or maybe across the street and you can still see the same lamp through a window, the light gets dimmer as you get farther away. It doesn't hurt near as much. If we were to set up colonies, say, on the moons of Jupiter, which is one thing that's been proposed, the sunlight would be a lot less, or would be weaker out there, and so we could use mirrors on satellites to try and collect more of it and kind of focus it in some, almost like using a magnifying glass to intensify the light rays of the sun here on Earth. Okay, so that's a little bit of background on this. We also have 2 satellites. The idea on this is that they were launched as one vehicle from Earth, and as they came in towards the Moon, they actually pushed off of one another, one going to one side of the Moon and one going to the other side of the Moon to start their orbits. That would result in one of the satellites being a prograde orbit. In other words, it spins the same direction as the central object, in this case the Moon, and the other one having a retrograde orbit where it would be spinning the opposite direction of the Moon. Now, if we were trying to be far more realistic, then in our limitations, your prograde orbit and your retrograde orbits would have to have kind of opposite, basically mirror image on their inclinations. On this, to keep it simple, we're asking that you just make certain that your orbit is prograde for pro-ISAT, so presumably between 0 degrees and 90 degrees, and then retrograde for ReadySat, the retrograde orbit satellite, and then have that one where it has an orbital inclination above 90. In this case, you could have them both very close to 90 if that's something that you wanted, and that wouldn't necessarily reflect real life, but for simplicity and what we're going for, we just require that the prograde satellite, pro-ISAT, have a prograde orbit, and that ReadySat have a retrograde orbit. You can read in the mission brief for more details on exactly what they are and are not allowed to have. If you exceed the scenario limitations, you may end up with a score of 0 or at least a penalty of some kind. Okay, we also have Tranquil Gardens, which is actually set up at Tranquility Base, at least that's where I tried to set it up, on the moon, where the Apollo 11 moon landing happened. All right, so in the far-flung future, we're trying to get sunlight there. One of the first things to understand about this is to set up and try and visualize what we're working with. And I've got a diagram, hopefully, to help visualize it. So here, we've got 3 different possibilities that I've drawn up. In the top one, we've got the bright side of the moon and the dark side of the moon, at this point in time, of course. And our target is on the not lit up side of the moon, currently. If you look at it in a couple of weeks, it would appear to be on the other side as the moon is moving through its orbit, and it would be lit up. So our goal, we've got the little triangle here, which is to represent our greenhouse. We want to get sun rays over to that. So we've got, here's the sun, not drawn to scale, but we have a light beam coming from the sun that can hit our satellite, represented by this purple rectangle to represent kind of a large mirror. And if we orient our satellite correctly, you don't have to worry about that, but if we orient it correctly, we could then reflect that light off of the satellite and then direct it down onto, say, the surface of the moon. Now, right now, I can't get the beam to go directly to the greenhouse because the surface of the moon is in the way. So one of the things that I've noticed with students when they first try and do this scenario, they understand that we need sunlight and that we need the satellite to be in sunlight to get its job done. But then I've watched a number of students focus on trying to get the satellite on this side of the moon so that it's nice and near the sun and in sunlight. And while that's great, we can see here that it won't be able to reflect light off of it down onto our target. So the middle one here is actually a representation of what we do want. We want a light beam coming straight from the sun to be able to come out, because light goes in straight lines, and hits our satellite, and our satellite is over here actually on the darker side of the moon, or the dark side of the moon in this case, and the light beam can hit it, be bounced off of it, and redirected down onto our greenhouse, which is what we want. But one thing that students run into an issue with, so I brought up this diagram to see the last part, you also have to be careful when you're on this dark side of the moon because you still need your satellite to have clear line of sight on the sun. If you try and bring it too low, as in directly behind the moon, say over here, we can see that the light rays from the sun, well, here's one of them where it can barely miss the side of the moon, and then on the opposite side of the moon, that basically creates a shadow over here where any light in between coming from the sun, you're in the shadow of the moon and you're actually not getting any sunlight. So you have to be careful about where you put your satellite in its orbit. Hint, hint, this may have something to do with the inclinations that you all are going to be choosing. So we've got what would be a beam of light that comes straight from the sun and goes over to our satellite, but we can see here it would actually be stopped by the moon. We're in the moon's shadow. And because the satellite is not receiving any light, it can't reflect any of it back down to the greenhouse. So you're looking to have your satellite on the dark side of the moon, but also make certain that it stays out of the shadow of the moon. Now, that's describing one satellite. You actually need that to happen for both of the satellites, and that's a key part of working with this scenario. So this is one that while you have only a handful of limitations on your orbital inclination, you are required to have prograde for pro-ISAT and retrograde for ReadySat, but there are built-in limitations that aren't explicitly told to you, basically some inclinations that aren't going to do a good job of solving this scenario. I'm not going to talk too much more about this in particular, though I will bring up a few things that we can take a look at. First off, I'd like to give you the same advice that I've given in our previous lesson. There are a couple things that we definitely want. We want the access time, is how we're checking this, between Tranquil Gardens and Pro ISAT. I'm going to bring up that access time. And we also want the access time between ReadySat. You could have gone over here and right-clicked on it, but I'm just going to switch it there, and Tranquil Gardens. We basically need to see the times for 2 targets this time. So I've got both of these. The default numbers that are coming up, if I scroll down and go over, we've got, this is in hours, I believe. Yeah. So ReadySat right now in the default orbit gets 7.27 hours, and then Pro ISAT, comes down, and we have about 7.314. So they don't have exactly the same times, but they're fairly close to one another because their initial orbits are very similar. Now, these are the 2 numbers that we care about. We add those 2 numbers together to get our total score for this scenario, but when you read the, wrong button. When you read the mission brief on this, it does also say that you need a score, you don't start getting points until you're above, I believe, 40 hours or so. So you would need to go through and try and get these numbers as big as you can. Now, a big part on that is, let me finish up what I was saying. We're going to be changing some things around, so I'm also going to need to adjust the settings of Pro ISAT and ReadySat for that matter. But one thing that you might consider doing is maybe taking this one at a time. And so I've brought up the ReadySat access, but I'm going to minimize that. Maybe I start by trying to see what can get one satellite working well, and then try and mimic that for the other, because we have a lot of mirror type aspect of this. One of the things that I'm going to recommend, like I did before, we're going to need to change our satellite, so I need the orbit information up. I'd also like to be able to visualize what I'm working with, so I'm going to keep my 3D up. You could keep the 2D up, but we also want our access time. I heavily recommend going to Window and tile, say, vertically, and then I can go through and find each of my windows. So for here, I can zoom out a little bit on my 3D graph. And let's say that I want to try and get a little bit more time on this. Maybe I want to take it out to a higher apogee. So I'm going to do 1000 as my apogee instead. When I click apply, I can see that my orbit has gotten a little bit bigger, although on one side more so than the other. That being said, I've made a change. I could go through and keep track of that in my spreadsheet, and then I can come over here to my report and click refresh, and I can see, hey, that did actually help quite a bit. I went from 7 hours up to a little under 14 hours. Well, maybe bringing the apogee up did that. Let's try adjusting the perigee, and here it will yell at me like usual. This is the first time I've opened it. I'm going to go back down, do our little trick to fix it, switch away, but then come back, and apply. Don't click OK because it'll close the window, just click apply. And now we can see that I've got a much larger circular orbit. And the perigee helped a little bit. I gained a little bit more time, but I'm now at just under 15 hours for this one satellite. We can go through and we can play around with this, but one thing that I would bring up is we've already talked about the importance of an elliptical orbit. An elliptical orbit you can have by having a different perigee and a different apogee. One of the things that can be very useful on that is when, let's go ahead and take a look, maybe if I were to drop this down to maybe 200 kilometers perigee, so I have a highly elliptical orbit. Let's look from above. I'm going to press play. And we can see that we move real fast. We're looking at the purple satellite when it's close in, and then as we start going further out, it's going to slow down. So one thing you want to ask yourself is this: is there a place where I want the satellite in the orbit to go slowly in comparison to the moon, and what things can I alter in order to make that happen? Well, we can get an elliptical orbit, and then it's up to you to kind of determine what side of the moon you want it to be moving fast or slow on. I will remind you that you can move where the closest point is by adjusting the argument of perigee. There's a little bit more that I wanted to talk about in regards to this particular scenario. I will remind you that depending on what your orbital inclination is, when you're on the dark side of the moon, where you want to be to try and reflect sunlight onto your target, you might have it where the moon itself is blocking your access to the sun. So you might consider that when it comes to your inclination. One of the last things that I'll bring up is this before we move on to the other part that we wanted to take a look at in this lesson. This scenario has it specifically that the satellite contact time is only good if the satellite is in sunlight. Well, I've actually already programmed that in. I've heard from a number of students that said that they were a little concerned about it and wondered if they had to manually check that. I'll show you where that's at. We can go to ReadySat, for instance, and go down to Properties. And while we have the basic orbital information, what I'm actually looking for this time is going to be most of the way down where it says Constraints. Now I can go to the constraints. I'm going to blow this up so we can see the full thing. I haven't enabled any constraints on azimuth, elevation, range, or anything like that. That takes into account angles or distances. We might have a maximum or minimum range. Hint, hint, you'll be seeing that soon. But if you go to sun, this one deals with lighting. And I've selected lighting, and I say that the satellite only works when it is in direct sunlight. I could change it where it only works when it's in shadow, umbra, or that it only works when it's in penumbra, partial sunlight. In this case, for the limitations of our scenario, we want direct sunlight, and that's what I've got programmed in. But I wanted to show you that that's already built into the scenario, so you don't have to add it, and you don't have to micromanage it. But if you were going to make a similar scenario, you might need to put that in. Or if it wasn't added in, this is where you could add that. Okay, so that's most of the key things that I wanted to show you for the first scenario in this series. Let's take a look at the second scenario, relay delayed. Now, I've actually already adjusted this a little bit. Let me bring this back to what it started as by default, 28.5 degrees orbital inclination. That's the default when you just insert a standard object for the satellite. It puts it at that orbit. Let's see. So we've got two targets, one in North America and one down in South America. One thing that I wanted to talk briefly on this is looking at other types of constraints. Now in this one, we have it where we're collecting information in South America and then we want to relay it to North America. Read over that in our mission brief, but order kind of matters in this, and if I were being very realistic, we would have to keep track of, okay, on Monday, South America gets this much information, and then limiting how much of that's the maximum that you could then transmit over to North America after Monday. I'm keeping this one a little bit simpler. We're actually going to take a closer look at being more precise about it in our QR2 series, when we'll be looking at budgeting things like data budgets, among other things. So for this, we have some limitations in there, but I have set it up where basically South America begins its contacts a little bit before North America does, and ends theirs before North America. So that's supposed to reflect, okay, the information is being collected in South America, goes up to your satellite, and then it can be sent back down to North America. Well, I have some of that already programmed in. If I right-click and go to Properties on the ground station, we've got all of its usual information, its latitude and longitude and all of that, but if I go to its constraints, I don't have anything on range or anything like that. That's the basic. On sun, I don't actually care if it's in light or dark. But the next one down is called temporal. That's a fancy word for time-based. And I've actually set up intervals, and I've selected use these versus you could exclude intervals. So basically, I say that this site is up and running and can be contacted from 9th of June to 22nd of June. I could switch that around and say exclude intervals, where it would say, hey, as this is the one time that it can't be reached. But I've built in the time limitations on this. I've done the same thing with OU, our target in North America, that would be receiving the information later, except I have it running from the day after for both of those. So that's to set up the idea that the information has to be collected in South America, then it can be sent up to the satellite, and only then could it then be sent down to North America. I once again have built those into our actual scenario. We also have on, say, the satellite, or even the installations themselves, you could have on the constraints basic, we can do angles, but we can also do a range over here, or maybe if you get far enough away, the signal won't be strong enough and it can't be used. You'll be seeing that on some of our future scenarios, and that's a place where you can program those in. Okay, one of the last things that I wanted to mention, and this one doesn't necessarily apply to this scenario, but it might be useful for one of the others in this series. I'm going to take us up to a higher inclination, say 70 degrees. We can see that I've gone much more northward, southward. One of the things that I wanted to point out on this, because it's had applications in a variety of scenarios that we've seen over the years. When you look at the 2D track on the ground, we can see that for almost a quarter, maybe a third almost of the orbit, our satellite is going to hang out at its maximum value for the inclination. So I set it to 70 degrees. We can see that from here over to here, it's at about -60. It's at 60 degrees. In other words, it's at a very southern latitude. And this is about a quarter of its orbit. It's hanging out very far south. We've also got the same thing for very far north. For about a quarter of its orbit, it's around, say, -60 or +60 up to 70. We hang out a lot at the north and south extremes. But around the equator, we're there for only a very short amount of time. So let me press play on this. In fact, we'll go to the big screen on this, and I'm going to press play. I'm going to speed it up just a little bit, but we've got very far north, very far north, very far north, very far north, and then now for a very short amount of time, okay, we're by the equator, but then we're gone from the equator pretty quickly. Then very far south, very far south, very far south, very far south, and then going on these latitudes that are in between, we're actually going past them relatively quickly. We do not spend very long over the equator itself. Now, because of how line of sight works, we might still get good signal over the equator, but I wanted to emphasize that a lot of your time in your orbit, based on your inclination, is spent near the highest, farthest north, and lowest, farthest south values. That's something to take into account, and a benefit that you could get from a high inclination orbit if you wanted to make certain that your satellite spends a good amount of time in one part of its orbit versus another. When you combine that with the idea of an elliptical orbit, you can actually control times a lot more than you might think. All right, those were the key main topics that I wanted to introduce to help support these particular scenarios, including the constraints so that you knew what was and was not built in, definitely the diagrams so that you could kind of visualize what was happening in the very first scenario, and as you go through later scenarios, drawing a diagram like this of your own so you can visualize the problem is something that I heavily recommend and can help you solve a lot of problems much more easily. All right, hopefully this video was useful for you.